Okay, starting from this week, we are going to read this book, Kalman Filtering with Real-Time Applications Together. So chapter 1 is basically about some preliminary results. Okay. So today I will talk about section 1.1. It's basically about matrices. So first it gives some definitions of vector. Okay, vector is column vector. Then it gives the definition of a matrix. So a matrix is positive definite. So if you use the vector x transpose times a x, it's a number. Okay, if the number is positive number, so for non-zero vectors x, so we say this matrix positive definite. Okay. So can you all see my screen?
Yeah, I can see.
Okay. So then if some chat, okay, good. Then if x transpose ax is non-negative for any vector x, it is said non-negative definite. But I don't like the name. In general, normally I think that you should call it, positive semi-definite. I think most people call it positive semi-definite. Okay, I will use the name positive semi-definite. So something you need to pay attention that the A matrix. Okay, someone cannot hear. Can you all hear me? Can you all hear me?
Yeah, I can hear you.
Okay, then I will continue. Okay. So something you have to pay attention that A matrix may not be symmetric. So then it introduced the notation matrix A is greater than matrix B. Basically, it means that the matrix A minus B is positive definite. Another notation, A matrix is greater or equal to B, means A minus B is non-negative definite. So it's positive semi-definite. Okay. I will use the name positive semi-definite. So next, it introduced the Schwarz inequality. So how to understand the Schwarz inequality? So let me go to the comment. Okay, open the comment. So how to understand the Schwarz inequality? We have two vectors. Let me draw two vectors. So this is vector, let's say this vector x. So this is a vector y. Okay. So this here, the left-hand side is the inner product. The inner product is x transpose y and sides of x transpose y. So what we can do, we can project y to x. So let me use the notation projection of y to x. Okay. Then I can project y here. So this vector will be projection of y to orthogonal space of x. So by inner product, we know this vector times x is 0. So the inner product x transpose y is only this vector times the vector x, then the size, okay? The size of this vector times the size of this vector. Of course, it's less than the size of x times the size of y. So this is the geometric interpretation of the Schwarz inequality. So here it means two norm, the inner product and the vector two norm. So when it becomes equal, it's very easy to see if the vector y is the same direction with x or opposite direction. So the Schwarz inequality becomes equality. So this is another way to write the Schwarz inequality. Basically, take square on both sides. Okay? So this is the square of x norm, the square of y norm. Because this is a number, you can put it in the right-hand side. So this is the square of x transpose y. It's interesting, you can change, if you choose the x to q and y to p, you get the matrix Schwarz inequality. So the p and q may not be square matrix or may not be symmetric, but only requirement the p transpose p is non-singular. Then you have the matrix Schwarz inequality. So in this form. So this inequality becomes equality if there exists some matrix S. So Q is equal to P times S. So I'm not talking about the proof, okay? So you can look at the proof by yourself. Let's move on to the next lemma. I think there are total 10 lemmas in section 1.1. So the second lemma is the matrix inversion lemma. So basically, if we have a matrix, we can decompose the matrix to the blocks. So the inverse of A can be written in two different forms. This form or this form, okay? So particularly you can use the inverse, okay? Write the inverse to this form. I think this form is very useful in Kalman filter in various sensor networks, because this form I think is corresponding to the information form of the Kalman filter. So I will not talk too much about this. You have to remember this. Then something I want to mention is here. Okay? So this one usually called Schur complement. Okay? If I write the text here. So this is called Schur complement. So if the A11 and A22 are non-singular submatrices, okay? They are Schur complements. They are very useful matrices. Then if A can be partitioned in this block matrix form, then the determinant of A can be written as determinant of A11, then times the determinant of the Schur complement. Basically, you're starting from here, A22 minus A12, A11 inverse A12. So another form will be determinant of A22, then times determinant of the Schur complement will be A11 minus A12, A22 inverse A21. So that's the matrix inversion lemma. So I will not show you the proof. Let's move on to the next one. So the third one is very interesting because it doesn't require the matrix P and Q to be symmetric. If it's symmetric, the proof should be very easy. But if that's not symmetric, if P is greater than or equal to Q is greater than 0, then Q inverse is greater or equal to P inverse, greater than 0. So here, we do not require P or Q to be symmetric. So then we move on to about the trace of the A. The trace of a matrix is just the sum of its diagonal elements. Okay. Here's the formula of the trace. And then we have this lemma 1.4. If A, B are n by n matrix, then we know the trace of A transpose is the same with the trace of A, because when you do the transpose, you do not change the diagonal elements. The second one is trace A plus B is equal to trace A plus trace B. So we call it additivity property. This additivity property. Okay. So the second one is trace. If a scalar lambda times A is lambda times trace A. So this is homogeneity. So if we consider the trace as an operator, then we know we combine these two. So we know the trace satisfies the principle of superposition. Basically means if something satisfies the superposition, basically means it is a linear. Basically, if you consider the trace as an operator, it's a linear operator. Then if A is n by m matrix and B is m by n, then we have trace AB is a trace B transpose A transpose. I think it's just directly apply the result trace A transpose to trace A. But this one, trace A is trace A times B is the same with trace B times A. Yeah, need some proof, but change the trace A times B will be the sum of Aij times Bji, and you just change the index I and j, you know trace A times B is trace B times A. Again, you use the transpose property, you get trace BA is a trace A transpose B transpose. Then the last one is trace A transpose is all the elements Aij squared, and then you take the sum. So there's an exercise 1.1 to prove lemma 1.4, then you can do it afterward. So lemma 1.5, it says if A is an n by n, so here is a square matrix with eigenvalues lambda 1 to lambda n. So here it says the lambda 1 to lambda n, they may contain the same eigenvalues. So the trace A will be the sum of all eigenvalues. So I will not show you the proof. Yeah. So it follows from this lemma. So we know if the matrix A is greater than 0, this means A, then all its eigenvalues are greater than 0. Then of course the trace A is greater than 0 because it's the sum of the eigenvalues. So if a matrix A is positive semi-definite, then the trace A is greater or equal to 0. directly follows from lemma 1.5.